Okay, Newton's first law, objects in motion stay in motion in a straight line at a constant speed unless acted upon by an unbalanced force. Newton's second law. Force equals mass times acceleration. Newton's third law. For every action, there is an equal and opposite reaction. And the action and the reaction, these are forces. So something might be really fast and the reaction might be really slow, but they're the same amount of force. If something is really fast and it is acted upon by the same force as something that's really slow, then the slow thing must be bigger, more massive. It must have more inertia. Inertia is resistance to change in motion. If something has a lot of inertia, then it's hard to get it moving and it's hard to stop it once it's moving. And the more mass something has, the more inertia it has. 1 Newton is about a quarter of a pound. It's really 0.224 pounds. Kilogram is about 2 pounds. It's really closer to 2.2 pounds. A Newton is a unit of force, and a kilogram is a unit of mass. They're used interchangeably. If you go to space, outer space, you have 0 newtons of weight, but you still have just as many kilograms of mass as you've ever had. Number 13. Let me zoom in a little bit. Yeah. Where's the top? Right there. Right there. Okay. Sorry for the interruption. So, 13 through 17. This is some vehicle that's starting here and following this course, and we're supposed to tell whether it's forces acting on it are balanced or unbalanced. So it sits still at A for 10 minutes. If it's sitting still, forces are balanced. Basically, they're balanced whenever there is no change in motion. So if you're sitting still, your motion's not changing. You were sitting still before, you're still sitting still. Between A and B, it's speeding up from 0 to 20. So there is a change in motion, which means forces are unbalanced. It's accelerating. From B to C, it's going at a constant speed in a straight line, so the motion is staying the same. The speed's not changing, the direction is not changing, there's no change in motion, so the forces are balanced. Going around this corner, it's going at a constant speed, but the motion is changing because the direction is changing. Speed's not changing, but direction is. And if there's a change in motion, the forces are unbalanced. From D to E, it's slowing down, so the forces are unbalanced. The motion is changing. Suppose the forces acting on a car are balanced. If this is true, there are only 2 things the car could be doing. It could be sitting still, and it could be moving at a constant speed in a straight line. If it's doing anything other than these 2 things, then the forces are unbalanced. Suppose the forces acting on a car are unbalanced. So what are the things it could be doing there? It could be speeding up, so I'll put accelerating. That would be a change in motion. It could be slowing down, so it could be decelerating. That's a change in motion. And it could also be turning. Or it could be turning and decelerating, or turning and accelerating. That's the first page. Page 2. The ball is sitting motionless on the ground. So here's a ball, here's the ground. The ground is applying an upward force of 20 newtons to the ball. So I'm going to draw that, 20 newtons. What do you know about the net force acting on the ball? Well, if it's motionless, that means it's sitting still, so the forces are balanced. So the net force, if forces are balanced, so that means that the weight of the ball must be pushing down with a 20 Newton force also. So the net force is 0 newtons. Anytime the forces are balanced, the net force is 0. So that's the answer. That's what we know. 21. F equals ma. If this is true, what should happen to the acceleration of an object if you double the force you're applying to it? Well, it should, the acceleration should double. Acceleration doubles. And a way to see this is if you have, I'm just going to write F equals ma. Now, that means force equals mass times acceleration. If I make the acceleration bigger, multiply the same number by a bigger number, now this force is going to be really big too. Okay. B, what should happen to the acceleration of an object if you apply the same force but you double the object's mass? So in that case, that would be like saying this. Started out with F equals ma, now I'm going to double the mass. Oop. You keep this force small, make it a big mass. Now if that force is going to be little, and I made this mass a lot bigger, then in order to multiply these two and keep that small, the acceleration has to be small. If you think about that, if you make something twice as heavy, twice as massive, it's going to be twice as hard to accelerate. So the acceleration, acceleration decreases by half. So try to push something that's twice as massive and you're only going to be able to accelerate it half as fast. C, if you want to accelerate something twice as fast, how much force should you use? Well, twice as much. Again, we can use this formula to see that. If we start out with, if we compare it to just a mass times an acceleration, but now I want it to accelerate twice as fast, so I want a big acceleration. That means force is going to be big too. I already did that up here. Make acceleration bigger, force has got to be bigger. If you want an object to accelerate twice as fast when the same force is applied, what should you do to the mass? Well, if you want to make it go faster and you're not going to push any harder, then it has to have less mass. Mass, I'm going to say, must decrease by a half again. So comparing it to this equation, we've got a force equals a mass times the acceleration. If we want twice the acceleration and the same force, so now we've got big acceleration, same force, that means we have to have a tiny little mass, because if you multiply a big number by a normal number, you're going to get a big force. So this has to be a little mass. You can think about the equation. The equation is sort of the proof for all of these, but this should make common sense. I'm going to run back through them quickly. So if you double the force on something, it's going to accelerate twice as fast. If you apply the same force and you make something heavier, it's going to accelerate slower. If you want to make something go twice as fast, you have to use twice as much force. If you want to make something go twice as fast, but you want to apply the same force, then that thing has to be half the mass. Alright, now we've got mass, volume, weight. Mass is the amount of stuff in an object. So I look at these, this is big, but that doesn't mean it has the most mass. This one has the most stuff in it. It's got 4 of those dots there. So it has the most mass. Volume is size. So the one that's biggest is B. Now the one that weighs the least is also going to be the one with the least amount of stuff. Weight is the force of gravity, and gravity applies more force to things that have more stuff in them. Gravity works on stuff. The one with the most stuff in it is E, but that's not the question. The question is which one weighs the least. A is going to weigh the least. It's not the smallest, but it's got the least stuff in it. Weight is the force of gravity acting on an object. Number 26. A 1,000 kilogram car accelerates at a rate of 6 meters per second per second. What's the net force acting on the car? Well, we use Newton's second law, the force formula. So it's the car's mass, 1,000 kilograms, multiplied by the car's acceleration, 6 meters per second squared. We get 6,000, and the units are newtons. On planet Z, falling objects accelerate this fast, 32 meters per second squared. How much does a 90 kilogram man weigh on planet Y? It should say Z. That would be an unfair question. So weight is the force of gravity, so we just use this formula. Force equals mass times acceleration. 90 kilograms is the man's mass. We multiply that by the acceleration. 90 times 32, let me pull out my trusty calculator here. 90 times 32. 2,880 newtons. Number 28. A 100 kilogram man is falling from the sky on Earth. Use F equals ma to calculate the weight of the man in newtons. You need to know a little bit of information here. The weight is the force of gravity. So force equals mass times acceleration. 100 kilograms is the man's mass, but the acceleration, we're not given that. In the previous question we were given that. It said falling objects accelerate at this rate. You have to know that on Earth, the acceleration of gravity is 10 meters per second squared. So I'll just put that in, 10 meters per second squared. This is the man's mass. This is the man's acceleration. That's the acceleration of anything on the Earth. 100 times 10 is 1,000 newtons. A woman is falling at terminal velocity. Here she is. She's falling from the sky, falling downward. This shows that she's moving down. That's the little lines of wind blowing up past her. Force of air resistance pushing her upward is 500 newtons. I'm going to draw it off to the side. How much does she weigh? So we've got two things acting on her. One is air resistance, and the other is her weight, gravity. Weight is the force of gravity. And this is an easy question because we know at terminal velocity she's not going to accelerate anymore. At terminal velocity there's no net force. At terminal velocity these two forces are balanced, and what that means is this has to be 500 newtons. So how much does she weigh? 500 newtons. I'm gonna start a new video here.